Okay, so welcome back from vacations. What I want to do today, let me start with a general comment. Remember that a lot of time, machine learning models or machine learning methods, if you like neural network, SVM, decision tree, whatever, they solve under the hood. They solve an optimization problem. So there's some target function that we want to minimize, and the optimization problem may be constrained or not constrained, and maybe convex, so it has a unique solution, maybe non-convex, and then we use we can approximate the partial derivatives. We may not be able to approximate it. We may be able to calculate it, precisely, like in neural network using the backward propagation. And essentially, what we end up with is some optimization problem that we want to solve numerically in one way or not, or the other. And that hopefully gives us something that generalizes well. So that's the tricky part. So although we are solving an optimization problem, it may be that it doesn't give us good generalization. So we need to handle that as well. So machine learning doesn't reduce to optimization problems, machine learning algorithm, but it's a very important part of machine learning algorithm, the optimization problem and solving it, approximating. So this is the background for what we're going to do today. Are there any questions here?
Not yet.
Okay. So what I want to do today, maybe you ran into that when you start talking about optimization problem, and now it's clear for us why we want to do that, because we're interested in machine learning. One of the things that you run into is well, you need to solve optimization problem with many variables, and some of the intuitions we're used to doesn't work with many variables. But then the basic of solving optimization problems with many variables has to do with things that are generalization of things that we've seen in one variable, which is taking the derivative and equating it to 0 to find a local minima, and then determining if it's a global minima, and so on. All of that is a useful basis to understanding a optimization, numerical optimization in general, which is a vast area. And today we're going to just focus on a very specific aspect of this, which has to do with determining of whether or not a function has a local minima or a global minima. And I want to make a connection between the notion of a positive definite matrix and the notion of a local minimum. So this is the objective today. Questions? Is the objective clear?
Yes, it is.
Great. Okay. So let's start with a very simple examples, and that will tell us everything. You can generalize by yourself, so to speak. So let's take a nice function from R2 to R. In general, it's RK to R. And not by nice we mean that all the partial derivatives are continuous. Specifically, it would mean in our case that the partial derivative of x by y and then of f by y and then x is equal to the partial derivative of f by x and then y. Okay, the order doesn't matter. And so we take a function of two variables and we look at the Taylor approximation of the function in an area that is very close to a point. So we fix a point AB and we look at the Taylor expansion close to that point. So it looks, the way it looked in one variable, it looks very similar. That's just a generalization of what we're used to. So it's the function at AB plus we expect the the derivative times the point, which in two variables is x minus a, the partial derivative of x at AB, y minus b, the partial derivative by y at AB. So that up to here, this is the linear part of the Taylor expansion. And then I continue and expand it to the second degree, and I get 1 over 2 factorial of x minus a to the square of 2 partial derivative by x.
Why is the factorial needed? I mean, 2 factorial is 2.
Not needed. just when it will, next expansion will be 3 factorial and then it will be needed.
Okay.
Okay, and then 4 factorial and so on. It's the same thing. That's my point. Sorry. Technical difficulty. Okay. So and then plus 2 times x minus a, x minus y minus b, the partial derivative of f by x and then by y. Because the order doesn't matter, we I said 2 times this, okay? Because the order doesn't matter whether you take the derivative of y first or x first. The same thing. And then y minus b, that's square of 2, partial derivative of f by y and then by 1. Okay? And this is a good approximation if R is small enough at a ball around AB, basically, of radius R. Is that clear up to now?
Mm-hmm.
Okay, so what I want you to notice, and this is what I wanted to talk about basically. I wanted us to notice now the relation between this and matrix operation. And we'll see a matrix now that has to be positive definite in order for this to be a minimum, which is what I want you to see later. So basically, first thing I want you to notice is that the linear part is basically a scalar multiplication of two vectors. So I go and I denote x minus a, y minus b as dx dy, and the partial derivative of f by x at AB and by y at AB, this is the gradient f at AB. And if we take the scalar multiplication of these two vectors, we get the linear approximation. Okay? Make sense?
Yeah.
Okay. Now, if we look at this thing here inside the parentheses after the 1/2 factorial, all of this, then we can rewrite it as the multiplication of dx dy times this matrix and dx dy. And you need to notice that this matrix is what is sometimes called the Hessian matrix. Okay? So it's 2/2 matrix of all the different partial derivatives of all the. If you multiply this back using matrix multiplication, you get back to this thing inside here in the parentheses. So let's just see that. So if you multiply this by dx dy transpose, you get this here. So and multiplying, so this is a 2 by 1/2 vector times 2/2 vector. So if you multiply this, you get back just using matrix multiplication, you get back the same value, the same thing that you have here. So basically, you can think about the second order expansion as the multiplication of the Hessian matrix with this dx dy around them. Make sense? Yes, no?
Yes.
Okay, great. So here's the crucial point, okay? So if it's a local maxima, there's a necessary condition, right? So if it's a local maxima, then the scalar multiplication of the gradient and dx dy is going to be 0. So this part of the expansion goes away. Okay, this is 0. Now this part of the expansion is actually this. And basically, if we want this to be a minimum point, a local minima, then this needs to be greater than 0, right? If it's greater than 0, then fxy is going to be bigger than fab. So that's the reason. So basically, that's the reason this multiplication of the matrix and the vectors should be greater than 0. But that's exactly the definition of a positive definite matrix. Positive definite matrix is a matrix that multiplying it with the two vectors around it like that gives you something that is bigger than 0. And that applies not only to A and B. We want it to apply to any point in the ball, in the small ball around R, where the approximation is valid. So we are basically asking for more than what we need, because when you write the Taylor expansion here precisely, it will be some point in the ball, not necessarily A and B. So we will require that the matrix, the Hessian, is positive definite, actually requiring that for all points in the ball, it's bigger than 0. And then it's going to be also bigger than 0 for the special point. The Taylor expansion guarantees that we don't know which point it is, but that will guarantee that it's bigger than 0 here, which will mean that fxy is bigger than fab, which will mean it's a minimum. in this small ball, a local minimum. So basically, we see intuitively, we see the direct simple connection between the notion of positive definite matrix and the second order expansion of the Taylor series and the notion of the Hessian in a very simple example, which is easily generalized to any, just if you put a K here and you make the necessary modification, you'll get the same thing. And that's what I wanted to show. I wanted to show how intuitively the notion of positive definite is related to the notion of local minimum. Now, if you want to see, if you want to check yourself if you understood this, just try and now see if this is just one variable. What happens then? What is the requirements that you get for one variable? Someone sees it? So instead of R2, you have R. So what will the Hessian be in that case?
Even with one-on-one matrix.
Yes, it will be the second order derivative of f the 2, right? The second derivative, basically, right?
Yeah.
So what we are requiring then is that the second derivative is actually what? Because this will become a number, this will become a number, right?
Oh, right. Yes. This factor is only the
So if this is a number and this is a number and this is a number, it's commutative. So you get x squared here, and you get the second derivative. So x squared is positive, 2 factorial is positive, and the second derivative needs to be what in order for the point to be a minimum?
Eitan?
Say again? Okay, let me do it more slowly. So if R2 is now R, okay? Let's see how things changes here. So this becomes just a number, right? I mean a dx, and this becomes like a dx as well. And this is the second derivative, right?
Mm-hmm.
Okay, so I can reorder this and then I get dx squared and the second derivative over 2 factorial. And I still want it to be bigger than 0 for it to be a local minima, right?
Yes.
So what do I require on the second derivative? That's going to be what?
It won't be 0.
Yeah, it's going to be bigger than 0, right?
Yeah.
Okay, but then this is what we learned in high school, right?
Yeah.
We learned in high school that the second derivative, if the second derivative is bigger than 0 and the first derivative is 0, then the point is a local minima.
Mm-hmm.
Okay, so Yeah, so that's a way to, just remember and understand what we've done. A very fundamental, observations that then makes the notion of positive definite not mystical. But you see where it comes from. Okay, any questions or comments on this?
No, I need to think about this a little bit.
Okay, good.
About the first case. Also.
Okay. So yeah, think about it and contact me if needed.
Okay, thanks. Bye-bye.
Thanks. Bye-bye.